Alright, so hi everyone. You haven't seen me for a long time, most likely. The reason for that was I was making a bunch of things which right now I'm very proud of. So this is one of the big things that I was making, like big compared to whatever I've been doing for the past few years. So this is basically, I don't know what even call it. It's not just my notes on group theory, it's my notes made very intuitive and comprehensible. So I already posted two videos about this particular page, right? Group theory. And admittedly, in the second video, I didn't quite explain all of the things that I was learning. And this too is going to be a short video. I'm not going to explain anything because I expect that people will go on this page by their own and just start reading, because honestly there isn't much for me to talk about, right? But why am I making this video? So previously you would have seen that I updated the general group theory section, right? I put the fundamental theorems, not the fundamental theorems, it's what the isomorphism theorems of group theory in there. And now I've made another section which is an application. So we will be talking about the Rubik's Cube and how group theory is applied to the Rubik's Cube. But before that, I've made some more edits in general group theory, which is particularly conjugation and commutators. So there's a very nice video that goes in detail about commutators, which I've linked in this page. You can watch that video first, and that might give you an intuitive understanding of how commutators work and why are they so useful. It's almost magical. I mean, if you don't understand in detail what's happening, it does look very magical, right? So before that, let's go to conjugation. So when we conjugate, it's basically like a change of basis. So for people who have read linear algebra, you would know what a change of basis is, right? Well, it's something similar to that, except that the way we use that is that we only want some elements that we are permuting to be changed, so that we are involving some other elements which usually would not have been in the permutation. So for example, in a cube, if we are doing a down rotation, it only permutes all of the corner cubies in the down face, right? But if you conjugate that with the right rotation, what will happen is that all of the cubies in the down layer, well, their images, upon applying right on them, those images will be the ones that will be permuted. So in fact, one QB from the top layer will also be involved in the permutation, and one QB from the down layer is now not involved in the permutation anymore. The structure of the permutation, that still stays intact. So that's why conjugation is really useful, because it helps us generate all kinds of permutations with the same structure, right? Yeah, and conjugation also has these other properties that it like causes groups and all, but that particularly is not very useful in the context of solving a Rubik's cube. So we'll just read the conjugation of a permutation. So consider permutation P and Q, which are from the symmetry group on X, which is just a permutation group, okay? And suppose that P sends A, which is an element of X, to B, which is also an element of X, of course. Then it's easy to see that the conjugate permutation, which I'm denoting by F sub Q of P, which is Q inverse P of Q. Some people will write Q P Q inverse. It's the same idea. That will send Q inverse of A to Q inverse of P. So that's mainly what we will be using conjugation for. You have an original permutation P, you want to get another permutation with the same structure as P, but such that every element in P, I'm talking about element, it should be every element in the support of P, that is now mapped to some other element, right, which is given by Q inverse of A, right? Moreover, there's another theorem that says that when two permutations have the same structure, they are necessarily the conjugates of each other, of course, assuming they are from the same symmetry group. And what that means is you can in fact write all all permutations of the same structure as conjugates of some simpler permutation that you have. So once you have one permutation of a certain structure, you can get all the permutations of that same structure, right? And that's this theorem, which so the proof of that I'm not going to go for. Okay. And yeah, so in conclusion, we can say that two permutations are conjugates if and only if they have a similar structure, and that's really useful. So this is all that we want to read from conjugation. Oh, and by the way, I didn't explain what a support is. Support is just all the elements in X that are being changed by the permutation P. Alright, cool. Next we go through this thing called commutators. So commutator is something that takes in two inputs. So you are taking two permutations A and B. The commutator AB, so it's not necessarily permutations, it could be in some other context as well. You still talk about commutators, but we'll be talking about it in permutations only. So for AB being permutations, the commutator AB is given by this notation, which is actually not used, but this is what I came up with because I used the square bracket notation earlier. So yeah, it's given by this thing, which I'm defining to be A inverse, B inverse, A and B. So you first apply you first apply B, you apply A, and then you undo this, but in the wrong operation. So that hopefully does something. The reason we use commutators is because, say you have two very complicated permutations, and the only nice thing about them is that their supports are intersecting at a single QB. Well, I shouldn't say QB, but any element in fact. Then their commutator will be a 3 cycle, and that's really useful because you went from two complicated permutations to just a 3 cycle, right? That's useful. So you can generate 3 cycles like that, and 3 cycles have they are simpler to deal with, right? And they can be used to do a lot of stuff, right? So yeah, this is the thing. So the theorem is for non-identity permutations, if support of G intersected with support of H, that's a single element, then the commutator G and H of G and H, that is given by this 3 cycle. So it's the element that they agree on. Then you have G inverse of X, so the element that would be in place of X if you applied G on it, and then H inverse of X that would be in place of X if you applied H on it, right? So I'm not going to go over the proof once again, yeah, but this is important I guess while solving the cube. Okay, so now you understand about commutators, we can finally go to the actual Rubik's cube. Also, I updated some stuff in the internal direct product because I learned that there's a thing called semi-direct product, which is basically the internal direct product, but it's written in a different notation. It's written as x and whatever this thing is times y, right? Okay, now let's go to the Rubik's cube. So this is a fairly large chunk, so I'm just going to skim over all of it. First of all, I introduce to the cube and I show you some simulations, but honestly, if you are here for the cube, it's like for the algorithms, then you probably know all of it. This particular website is rather nice because it allows you to input all the moves just by typing them and then see the animation of these moves being performed on the solid state of cube, so you don't have to do things manually. And also it has some nice notation, so just head over to this and use it. And also this not this side particularly, also this side actually allows you to do operations on sequences, such as take their commutator or take their conjugate. So yeah, it is really nice. It's actually meant for what we are going to do. Okay, we aren't solving the cube, right? We aren't just solving the cube, we are figuring out how to solve the cube. Alright, so before solving the cube, we have to decide on some notation. How are we going to represent any state of the cube using numbers or some algebraic concept? So turns out that to represent a cube, there's a fairly popular way, that is you write the cube in a 4 tuple, which consists of these four objects: V, R, W, and S. V and W are permutations, and they are permutations of the corner QBs and the edge QBs, and R and S, they are vectors or arrays, I should say, which are basically like I shouldn't even say isomorphic. These are in fact z sub 3 cubed, as in there are 3 coordinates, each of them is like modulo 3. That's R by the way. And oh, this shouldn't be cubed, this should be 8 actually. Yeah, because there are 8 corners, so of course. And this is z sub 2 12 to the power of 12 edges, and each of them have 2 orientations. So read all of this to get an actual idea of what's going on, but the main idea is that you represent the cube algebraically with a 4 tuple, but most of the 4 tuples are in fact illegal, as in you can't actually have that 4 tuple, right, whatever it's representing, right, the state of the cube that it's representing, you can't actually get to that state without doing something that's not supposed to be done. So the only basic operations you can do on the cube is, the 12 basic operations: rotate front clockwise, anti-clockwise, right clockwise, anti-clockwise, all that stuff, right? Rotate slices basically. If you do something weird like twist a corner, some cubes allow you to do that, then that's an illegal move. You can't do that, right? That's not the way it's supposed to be solved. And so you would end up getting in something that's not solvable by legal moves, and it's part of this group, or part of some group that's isomorphic to this group, I should say. Yeah, and that's represented by some 4 tuple which is not legal. So we would like to know when is a 4 tuple legal, and to do that we basically derive the fundamental theorem of cubing. No, I think it's called cube theory, right? Or cubology, I don't know, I don't think it has a good name yet, but anyway, you basically derive that, and there are actually a bunch of PDFs online where you can look for the derivation, although they never go into the deep derivation, because most probably this kind of stuff is searched by cubers and not math people. But yeah, I'm going to go into the full derivation, of course. I mean, hopefully it's full. If there's some flaw in that, I don't know. And to do that derivation, you actually need to know some things about commutators and cycles, and something about the alternating group, like representing even permutations as 3 cycles and all that, which you learn on the way, of course. I mean, those are like some nuggets thrown in just so that you can continue, right? We define how do we combine 2 states together. Every state is also a permutation of the solved state, so you can think of every state being the permutation itself, as in the sequence of operations you did on it. So the way you combine 2 states or permutations, both are basically the same in this context, is by doing something like this. So the permutations of corners and edges, well, you just combine them the usual function composition way. For the orientations, it's slightly more complicated, because whatever happens on the second move x2 that you're doing, that's actually dependent on what the first move did, how it permuted the corners, right? Because that's important. Like, you have to know that to get the effect of doing R2, right? Some orientation change on the corners in this state, which is not solved anymore. So that's why we have this P of V1 thing, which is, by the way, a matrix. And no, I'm not going to go too deep into that, because it's mostly useless. We never actually deal with the second and fourth thing at all. We only deal with the first and third, and once we are done with that, we just change the orientations without worrying about V1, V2 and W1, W2 at all. And so this is not very useful, in fact, just a heads up. So don't spend time on this stuff. Yeah, right. Also, in this particular thing that I've written, I'm using a right to left notation, as in you have to read from right to left the sequences that I'm writing down, So for example, if I write UF, what that means is that you do front rotation first and then the up rotation. But usually it's written as FU in the cubing community. So just a heads up, right? Yeah. So representing the cube algebraically. Fine. Then there are permutations of corners. We deal with, properties of these permutations, and the only real property that you want to know is that there exists, in fact, like, not exists, but all the 3 cycles of corner cubies, all of them are possible, and they can be used to unscramble or solve any permutation of the corners given to you. And I'm saying permutation of the corners only, talking nothing about the orientation. So for example, this thing is a 3 cycle which cycles 3 cubies on the top face, I think. Yeah, so that's permutations of corners, and really that's all you need to know right now. You should read this to get the details. Okay, then it's permutations of edges, which is pretty similar to what happens in permutation of corners, although I've cut down a lot of stuff because I think it's intuitively making sense once you've read this permutation of corner thing, and you can figure it out yourself. So once again, the same idea that you can build any 3 cycle of edges, yeah, and then you can use those to unscramble. Yeah, I think that's the word. I'm using the word invert everywhere, so I'm also going to use that as well. So you use those 3 cycles to invert any state that you have to the solved state. I shouldn't say the solved state, but the solved state in terms of the permutations of edges. Alright, cool. And then finally you go to the characteristics of a legal permutation. In this context, we're talking about permutations only. Alright, we're not considering what's happening to the orientations at all. We'll worry about that later on. So the thing is that every legal permutations must have the parity of V and W being the same. If that's the case, then you can invert the permutation by doing the 3 cycle thing that I told you. If that's not the case, then it's an illegal permutation and you can't do anything to get it back to the solved state. Okay, I mean any legal thing, of course. So when is the permutation legally invertible? That's basically what I talked about. Yeah, just that. Okay, and then we finally go to the orientation. So this is very, how do I say this? There's a lot of setup involved in there. First of all, there's this thing with labeling the faces of the cubies and then labeling them in a right-handed manner. Then you have to label it such that in this unsolved state, 0 is at a certain face, right? It's pointing in a certain direction or in some certain directions. So it can only point in the front direction or the back direction in case of corner cubies, or edge cubies it can point in the front, back, top and down in that particular order. So if it's possible that it can point to the front, make it point to the front, don't make it point to the top. So yeah, the priority order is that front, back and then top and down. Cool. Yeah, right. Yeah, and once again we can figure out 2 moves that are very useful, as in they do some simple operations algebraically, right? So simple operations on the cube itself, the way we see it, the basic operations, those aren't actually all that simple algebraically. So instead we figure out sequences like these which do something which is simpler to understand algebraically, right, and which we can use. So this thing particularly adds 1 and subtracts 1 from 2 cubies, right? And in fact it could be any 2 cubies because you can do some kind of conjugation and composition thing on this. But yeah, and also like symmetry arguments and all. And similarly over here, you are doing +1 and -1 to the coordinates of the vector s in this particular case because it's edges. Over here it would be the vector r, right? And what we can do is we can reduce the vectors r and s by doing these operations on different cubies, such that only the last coordinate of R and S um, is like, I mean, it's either 0 or it's something. So all the first um, like till the last coordinate, all of the coordinates are 0. That's what I'm saying, right? You can reduce it such that this happens. And in fact, the last coordinate will be the sum modulo 3 and modulo 2 of the coordinates, the original coordinates, yeah, summed up, of course, right? So that you'll understand when you read all of this in detail. Yeah, and that once again gives you some way to solve the orientation problem, right? Once you're done with the permutation thing, you still have to solve the orientation problem, right? So you solve that and then you finally solve the cube. But you can only solve that if your cube is in the legal state. So once again, it's something like an if and only if statement. And so finally, you have the full condition of the cube being solvable, and this is called the fundamental theorem of cube theory, I'm gonna call it, which is basically these three statements. So if V and W have the same parity, and this sum of coordinates is 0 modulo 3, and this sum of coordinates is 0 modulo 3. I should put this over there, mod 3, I think. Well, this is R, so R is for the corners, and S is for the edges, and it should be congruences over there. I'll change that some other day, right? So this is when the cube is solvable. Well, yeah, that's pretty much it. Yeah, and it's an if and only if condition once again, that if these three conditions are met, then we can solve the cube, and if they are not, we can't solve the cube, no matter what we do, legally, of course. And so that's it. There's also some stuff about the God number of cubes and all that, which I'm not going to go into, because apparently the way that people figure out the God number is through a computer program. So there's not much math involved in there. I mean, there might be math that makes the program more efficient, but that's it. So apparently that program took 35 years, 35 CPU years on some bank of computers that Google provided to some person. But yeah, we are not going to do that, of course. And you saw how big the illegal cube group is, right? Well, even though the legal cube group is smaller than that, it's only smaller by like some very small factors. So that's it. That's it. It's still a very big number, a huge number. And yeah, that's it, I guess. So I want to thank all the people who provided me resources for this thing. So most of the group theory that I've read till now, that has been from the Abstract Algebra playlist on YouTube by Michael Penn. And I wouldn't say it's like a very good playlist, but yeah, I just like that guy, so I did that first thing. Okay, I shouldn't be saying it's not a good playlist, that might be offending some people, but yeah, it's not very much organized. You'll see what I mean when you actually open the playlist. Everything's shuffled up, right? That's the main problem that I have with that. Okay, and the reason that I started reading group theory was, well, because it was part of a course that I have at ITGN, and the course is still going on. The first half is taught by Professor Neeldhara, whom I really just want to thank. Well, she pointed me out to, so she pointed me to this talk on the commutators that I linked in this page, and that was helpful as well. Yeah, so that's it. I'll see you guys next video. Bye.